You know that feeling when you decide to finally figure out a new project, and like an hour later, you're just staring at your screen?
Oh, yeah, totally.
You've got like 17 browser tabs open, and you are just completely overwhelmed.
Right.
I mean, you start out just wanting to understand, how to keep your lights on during a power outage, or maybe how to run a small fridge in a camper van.
Right, the simple stuff.
Exactly. But suddenly you're deep in this forum post that feels like it was written strictly for electrical engineers. Like you have all these terms flying at you. Inverters, charge controllers, amp hours, voltage drops.
It's a lot.
It really is.
Right.
And instead of feeling empowered to build something, you just end up with this massive headache.
Yeah, I mean, it is the ultimate information overload trap. The barrier to entry for solar power feels incredibly high to most beginners, purely because the language is just, it's so dense.
Yeah, but
People see wires and batteries, and they just automatically assume that, well, because it involves electricity, it must require a formal degree to understand.
Well, our mission for this deep dive is to completely shatter that assumption, and really demystify DIY solar power for you. We have gone through a big stack of comprehensive guides from Project Solar DIY, and we are going to extract the absolute best insights.
Yes, and we're going to prove that you do not need an engineering background to build a system that can keep your essentials running, whether that's, powering a road trip van or even running an entire off-grid cabin.
Yeah. And the core philosophy from these sources, like the compass that is going to guide us through all of this technical jargon, is actually beautifully simple.
It really is. Every single decision you make in a solar build traces back to a single linear flow of energy.
Right.
So our goal today is to map that flow, walk through some very simple back-of-the-napkin math, and frankly, bust some massive beginner myths along the way.
Sounds like a plan. So before we can build anything, we have to understand the anatomy of the system itself, right?
Yeah.
Because when you look at a finished setup with all the cables and boxes, it looks like a spaceship.
Oh, it completely looks like a spaceship.
But the sources emphasize that the energy really only makes 5 stops in one direction. They call it the sun-to-load flow.
Yeah, mapping that flow is step one. The energy starts naturally at the solar panels. I mean, their entire job is to catch sunlight and generate raw, unregulated DC or direct current electricity.
And raw is definitely the key word there, right? I mean, you cannot just plug your coffee maker directly into a solar panel.
No, definitely not.
Because the power fluctuating off those panels is wild, spiking and dropping with literally every passing cloud. Okay, let's unpack this. The sources use a rather brilliant analogy for the next stop on our flow.
I love this analogy.
Yeah, they call the next component the charge controller, the bouncer at the door of the club. The club in this case being your battery.
That analogy perfectly captures the mechanism at play because the charge controller is, frankly, perhaps the most underappreciated part of the entire system.
Really? Why is that?
Well, batteries are incredibly sensitive to voltage. If that raw spiking power from the solar panels just slammed directly into the chemical storage of the battery, it would physically cook it.
Oh, wow. So it literally destroys the battery.
Exactly. So the controller's job is to tame that wild voltage, feed it into the battery at a safe, steady rate, and physically block the batteries from leaking their stored power backward into the panels when the sun goes down.
Right. Making sure it's a one-way street. Now, the guides break down 2 main types of these bouncers, PWM and MPPT.
Yes, and the sources are practically screaming at us not to cheap out when choosing between those two.
Right. I know PWM stands for pulse width modulation, and it's kind of the older, cheaper tech.
Mm-hmm.
But how does it actually work compared to the newer stuff?
The PWM is very rudimentary. Imagine your solar panel is pushing out 18 volts of pressure, but your battery only needs about 14 volts to charge.
Okay.
A PWM controller simply chops off those extra 4 volts and throws them away.
Wait, it just throws the power away?
Yeah, it wastes that potential energy as heat. But what's fascinating here is how MPPT, maximum power point tracking, operates. It does not throw that extra voltage away.
What does it do with it then?
Instead, it physically converts that excess voltage into extra amps of current.
Oh, I see. So it's actively preserving the total amount of power coming in, just like changing its shape to fit the battery.
Precisely. It is essentially a smart computer that constantly adjusts the mathematical relationship between voltage and current hundreds of times a second.
That's incredibly smart.
Because of this, an MPPT controller squeezes significantly more usable power out of your panels, especially in less than perfect conditions like a cloudy day or, a low light winter afternoon.
So it's a foundational investment that basically pays for itself in harvested energy.
Without a doubt.
Okay, so we have our tamed power, and now it flows into the third stop, which is the absolute heart of the system, the battery storage. This is where the energy lives, so you can actually, turn a light on at midnight.
Right. And the DIY solar world is going through a massive shift right now regarding battery chemistry. Everyone is abandoning old school lead acid batteries like the ones in your car.
Right, the huge heavy ones.
Yeah, and they're moving to LiFePO4, which is lithium iron phosphate.
And the underlying reason for that shift, according to the guides, is all about this concept called the depth of discharge limit.
Exactly. Every battery has a floor. It's a percentage of power you cannot drop below without causing permanent chemical damage. With an old lead-acid battery, that limit is 50%.
50%, that's it.
Yeah, drawing it down further physically degrades the lead plates inside through a process called sulfation.
Meaning a massive, heavy 100 amp-hour lead-acid battery only actually gives you 50 usable amp-hours before you are basically ruining it.
Yes, you are paying for a massive box, but you're only allowed to use half of what is inside. It's wildly inefficient.
So how does the lithium one compare?
Well, with LiFePO4 chemistry, the molecules are incredibly stable. You can safely draw them down to 20% or even lower without hurting them.
That is a huge difference.
It really is. They give you vastly more usable capacity. They weigh a fraction of what lead acid weighs. They charge faster. And their lifespan is measured in decades rather than just years.
Wow. Okay, so we have this pool of perfectly stored DC power safely sitting in our lithium vault. But I have a problem.
What's the problem?
If I take my normal living room lamp or like my laptop charger and somehow wire it directly to that battery, it's not going to turn on.
No, it is not.
Because the battery is putting out direct current.
Right.
Just a steady, flat push of electricity.
Yeah.
But my house appliances want alternating current, AC power, where the electrical flow physically sloshes back and forth 60 times a second.
Right. They speak two completely different electrical languages.
Exactly. So we need a translator.
We do, and that is stop number 4. The inverter. The inverter bridges the gap. It takes that stored DC power from the battery and mechanically chops and flips it, converting it into the standard AC waveform that your normal household outlets expect.
Which brings us to stop number 5, which is just your devices, the things you actually want to turn on. I mean, the whole reason we are building this in the first place.
Exactly. So that's the 5 stops. Sun to panels, panels to controller, controller to battery, battery to inverter, and inverter to devices.
Once you visualize that simple one-way street, the intimidation factor really drops significantly.
It does. But knowing the hardware is kind of useless if you don't know what sizes to buy. You don't want to just log online and blindly purchase a random starter kit.
Right, because that's how you waste a lot of money.
Exactly. The sources reveal that properly sizing a system involves answering 3 questions in a very specific order, where each answer naturally dictates the math for the next.
Math without the spreadsheets. I like this. So step 1 is figuring out exactly what you are powering. No guessing here. You have to calculate your total daily watt hours. The formula is just the watts of the device multiplied by the hours it runs, multiplied by the quantity.
Let's use the van life example outlined in the text to ground this. Say you install a 12-volt refrigerator. It draws 45 watts.
Okay, 45 watts.
But we have to remember, a fridge does not run continuously. The compressor only cycles on when the internal temperature drops. So over a 24-hour period, it might only actively draw power for 8 hours.
Oh, right. So 45 watts multiplied by 8 hours, that gives us 360 watt hours.
Exactly. Then you tally up the rest of your life. You have some overhead LED lights running for a few hours in the evening, maybe 60 watt hours. A roof fan blowing all night, let's say 192 watt hours.
You charge a laptop and a couple of cell phones, and you add all of that up, and in this specific van example, you arrive at about 844 watt hours a day.
Right, and that 844 watt hours is your foundation. It dictates step 2, which is your battery size.
Okay, let me try this. If I know I need 844 watt hours to get through my day, I just go buy an 850 watt hour battery and call it done.
Right. Well, you could, assuming the sun shines perfectly every single day. But what happens tomorrow when a storm rolls in and it rains for 48 hours straight? Your solar panels produce nothing, your battery hits 0, your fridge shuts off, and your food spoils.
I see. I built a system with literally 0 margin for error.
Precisely. This is why you must calculate your days of autonomy. Like, how many days do you want to survive without any sun at all?
Makes sense.
For a van, maybe you want a day-and-a-half buffer. You multiply your daily use, 844, by 1.5.
Yeah.
That gives you 12,266 watt-hours.
Right.
Then you factor in that depth of discharge limit we defined earlier. Because it's a lithium battery, we divide that number by 0.8 to make sure we never drain it past that safe 20% floor. The result is the true real-world battery capacity you actually need to purchase.
And once the battery size is locked in, step 3 is sizing the solar array on the roof to actually refill it. You take your daily energy consumption and you divide it by the peak sun hours for your specific geographical location.
Yes, and peak sun hours is a crucial distinction. It doesn't just mean daylight.
Right.
It means the specific hours of the day when the sun is high enough and strong enough to generate maximum power. Then, the guides tell you to add a 20 to 25% buffer to your total.
And that buffer accounts for the realities of physics, right?
Right.
I mean, wires have resistance, panels get covered in dust, and inverters lose a little power as heat during that DC to AC translation.
Exactly. It is a brilliant domino effect. The daily load dictates the battery size, and the battery size dictates the solar array. It completely eliminates the guesswork.
I have to push back on one thing, though.
Oh,
Wait, why can't I just guess on the inverter? If I go buy a 1,000-watt inverter, shouldn't I just be able to plug in my 1,000-watt microwave, heat up a burrito, and call it a day? Like, why do I have to be so meticulous with this watt-hour math?
well, that assumption is exactly where beginners start small electrical fires.
Oh, wow.
Yes, you have to account for continuous watts versus surge watts. Your microwave might require 1,000 watts to run continuously, but the physical motor inside needs a massive jolt of energy just to start spinning.
To get going.
Right. When you first hit start, it might surge to pull 1,500 watts for 2 or 3 seconds. If your inverter does not have the internal headroom to handle that initial surge, the system overloads and shuts down instantly.
Okay, that makes sense.
But even more importantly, people fundamentally misunderstand the sheer volume of DC current happening behind the scenes to make that microwave run.
Wait, what is happening behind the scenes?
Think about the math. Power equals volts times amps. If you pull 1,000 watts of AC power out of an inverter, and that inverter is being fed by a standard 12-volt battery, you have to divide 1,000 by 12.
Okay.
Factoring in a little inefficiency, you are drawing roughly 93 amps of direct current out of that battery.
Wait, 93 amps? We'll put that in perspective for people. A standard wall outlet in a modern house trips the safety breaker at just 15 amps.
Yes.
You were telling me we are trying to shove 6 times the electrical traffic of a household wall outlet through a single cable in the back of a van.
Yes, exactly. And that volume of current generates immense physical heat. To push 93 amps safely without melting the insulation, you need copper cables as thick as your thumb.
That's terrifying.
It is. This reality is exactly why the sources discuss the 12-volt versus 24-volt debate.
Oh, I see where this is going. If we use the water pipe analogy for electricity, voltage is the water pressure, and amps are the volume of water flowing through the pipe.
Spot on. If you wire your battery bank to be 24 volts instead of 12 volts, you literally double the pressure. Because the pressure is doubled, you only need half the volume of water to do the exact same amount of work.
So that 93 amp draw instantly drops to around 46 amps.
Precisely.
Mm-hmm.
The whole system runs significantly cooler, and you can use much smaller, more flexible, and honestly cheaper copper wire.
So even with flawless math, beginners still manage to waste a ton of time and money by falling for common myths or trying to cut corners. The sources outline a few specific traps. They essentially call it a cheap tax.
The cheap tax is real. The most common trap is undersized batteries. Because those lithium batteries are the single most expensive component on the shopping list, people try to buy the absolute bare minimum, convincing themselves they will upgrade later.
Right.
But if you undersize it, you end up cycling that tiny battery incredibly deep every single day just to survive. You stress the chemistry, you kill its lifespan prematurely, and you end up having to buy it twice anyway.
Yeah, that defeats the whole purpose. Now, track number 2 is the more panels illusion. And this visual bias caught me completely off guard.
Oh, it gets everyone.
Yeah, beginners log online and see a 400-watt solar panel. They assume it's going to be the size of a barn door. It feels intimidating. So instead, they buy 300-watt panels because the physical dimensions just seem more manageable.
It is a profound misunderstanding of the hardware. The reality is that a 200-watt panel is really only marginally larger than a 100-watt panel.
Really?
Yeah. And if you choose to install three 100-watt panels, you have just created three separate sets of wiring, 3 times the electrical connections on your roof, more holes to drill for mounting, and substantially more points of potential failure.
So bolting down two 200-watt panels gives you more total power with a fraction of the physical hassle and risk.
Exactly.
Okay, here's where it gets really interesting. Trap number 3. The winter myth.
Ah, yes.
If you asked me yesterday, I would have assumed winter is the absolute worst enemy of a solar panel. I mean, you have snow, ice, freezing winds. It sounds like a recipe for a completely dead system.
It is highly counterintuitive, but when we look at the physics, the paradox is that cold temperatures actually boost the efficiency of photovoltaic cells.
Wait. How does freezing weather make an electrical panel better?
It comes down to atomic movement. Heat causes the silicon atoms inside the solar panel to vibrate wildly. When electrons try to flow through that silicon to create electrical current, they keep bumping into these vibrating atoms, losing energy as resistance.
Okay, so it's like trying to run full speed through a crowded room where everyone is dancing.
That's a perfect way to picture it. But cold temperatures freeze those silicon atoms in place. It stops the vibrations, creating a perfectly smooth, completely clear highway for the electrons to travel.
Oh, wow.
Yeah, a freezing, crystal clear winter morning will actually produce higher wattage spikes than a scorching 100-degree summer afternoon.
So the temperature itself isn't the villain at all. The real enemies of winter solar are just the shortened daylight hours and, physical snow piling up on the glass, blocking the sun.
Correct. And the sources outline a very practical physical fix for that. You simply need to tilt your panel array about 10 to 15 degrees steeper than your geographical latitude.
Ah, so it changes the angle.
Exactly. This steeper angle perfectly catches that low-hanging winter sun, and gravity does the rest of the work, helping heavy snow slide right off the smooth glass.
Okay, so we have busted the myths, we understand the physics of the 5 components, and we know how to do the math. What does all of this actually look like when you put it together in the real world? The guides outline 3 distinct starter tiers to help people visualize their goals.
Let's walk through them. Tier 1 is the emergency backup. This is a brilliant entry point for someone who just wants security. It typically consists of a single 200-watt panel, a 100-amp-hour LiFePO4 battery, and a 1,000-watt inverter.
And it is important to note that this is not just a toy to charge a cell phone. The guides point out that a setup like this can actually run a CPAP machine.
Right, a continuous positive airway pressure machine for sleep apnea.
Yeah, it can run that all night long. You can keep essential LED lighting on and run a radio or laptop for days during a grid blackout.
Yeah.
It's really about establishing baseline resilience.
Absolutely. Then you step up to Tier 2, which is the RV or van setup. This is where you're looking at around 400 watts of solar on the roof, a 200-amp-hour battery bank, and a robust 40-amp MPPT charge controller to manage it all.
This tier is where the system shifts from being a backup safety net to providing actual freedom, right? I mean, this is enough power to run that 12-volt compressor fridge we talked about, ventilation fans, and work laptops. You can comfortably live out of this system on the road.
You really can. And finally, we reach Tier 3, the small cabin.
Okay, the big one.
Yeah, this is serious daily off-grid living. We are talking 800 to 1,200 watts of solar, 400 amp hours of battery storage, and a heavy-duty 2,000 to 3,000 watt inverter. This runs a full-size kitchen fridge, a water well pump, and maybe even a small, highly efficient air conditioning unit.
And across all these tiers, the sources are incredibly specific about the gear they trust. They warn heavily against buying ultra-cheap, white-label electronics off the internet.
Oh, definitely.
They specifically praise Renogy for their solar panels, noting they have a massive track record for physical durability in the DIY community. And for the electronics, the brains of the operation, they highly recommend Victron energy components.
Yeah, the Victron recommendation is purely about the power of their digital ecosystem. The guides specifically highlight the Victron Smart Solar MPPT controllers and their Smart Shunt.
Right.
These devices have built-in Bluetooth, and they literally talk directly to each other. It gives you a unified real-time dashboard on your phone, showing exactly what your entire system is doing at any given second.
So what does this all mean? Well, the sources make this amazing point about why that Smart Shunt is so vital. A standard battery monitor just guesses your remaining power based on the battery's current voltage.
Which is terribly inaccurate.
Right, because voltage fluctuates constantly depending on what you've plugged in. but the smart shunt actually sits on the negative cable and physically counts every single electron flowing in from the sun and every single electron flowing out to your fridge.
Exactly.
Adding it to your system is like finally turning the lights on in a dark room. You completely stop guessing.
It gives you absolute certainty. And if we connect this to the bigger picture of DIY projects, the guides emphasize that certainty and safety are not optional extras. Proper fusing is non-negotiable.
Yeah, let's talk about that.
You must install a catastrophic fuse on your main positive cable within 7 to 12 inches of the battery terminal.
That's specific, huh?
Yes. That lithium battery holds an immense, frankly terrifying amount of resting energy. If a wire frays and shorts out somewhere in your van, that proper fuse right at the source will pop instantly, stopping the massive flow of current before the wire can melt and start a fire. Safety and accurate monitoring are the absolute foundation of this entire endeavor.
Well, we have really journeyed from the raw, chaotic nuclear energy of the sun, corralled it through a smart MPPT bouncer, stored it safely in a stable lithium vault without degrading the chemistry, and mechanically translated it into usable AC power for a house.
We have, and we've seen that the math to size it all properly is not an engineering exam. It's 30 minutes with a pen and paper.
Just multiplying and dividing.
Exactly. Calculating your daily loads, dividing to ensure you have days of autonomy for bad weather, and multiplying for your local sun hours.
And we learned how to avoid the traps. Like, don't starve the system with undersized batteries. Don't drill a dozen holes in your roof for tiny panels when 2 large ones will do perfectly fine.
Right.
And leverage the cold winter physics by just tilting your panels up a few degrees.
The overarching message synthesized from all of these sources is honestly incredibly empowering. Building a solar system is arguably one of the most deeply satisfying things you can accomplish with your own hands.
I can totally see that.
You are taking a tangible step from complete reliance on a fragile, centralized grid toward genuine, self-sustaining independence.
It really is profound when you strip away all the jargon, which leaves us with a fascinating final thought for you to mull over. Once you physically wire one of these systems up, once you look at your phone and see the actual math of your daily watt hours flowing in from the sun and flowing out to your devices, how does that alter your psychological relationship with the power in your home?
Wow, yeah. This raises an important question about modern convenience, right? When power is invisible and seemingly endless, coming from some mysterious power plant miles away, we just don't respect it. We just leave the lights on.
Exactly. Does physically generating your own power make you hyper-aware of every single switch you flip? Does watching the sun physically fill your battery shift you from being a mindless consumer of energy into a conscious, active manager of it?
That's a great perspective.
It is definitely something to think about the next time you find yourself with 17 browser tabs open, trying to make sense of a new project.
Yeah.
Maybe the ultimate goal isn't just to build a power system. Maybe the goal is to fundamentally change how you see power altogether.